Hello, and welcome back to Lecture 7 of the Foundations in Kinematic Analysis lecture series. In the previous lecture, you learned how to merge multiple data streams together. Today, we'll conduct our first kinematic analysis, examining the speed and velocity of a movement signal. We've got a few technical definitions in this lecture, and we'll go through them each one by one. So we'll start with a definition for position. Position refers to where an object is. And for this lecture series, the objects we're interested in are body landmarks, for example, the wrist. This video clip is an example of a gesture stroke that was annotated in an ELAN. In the plot below, you can see the trajectory of the speaker's wrist while he produces the stroke. His wrist first goes up, then comes all the way down, and then each point in the plot corresponds to the X and Y position of the right wrist at a given moment in time. We can define the starting and end position of the right wrist using the X and Y coordinates. For example, the starting position is at X equals negative 0.78 and Y equals positive 0.23. And the wrist is at this position at around 24 seconds into the video. Similarly, we can define the end position of the wrist. Next, we have distance. Distance is the total length of the path traveled. Distance is a scalar quantity, meaning it doesn't consider the direction of travel, but only the magnitude. For example, during a gesture, a wrist might travel a distance of half a meter in real-world space or 1.5 units in normalized coordinate space. To calculate the distance that the right wrist traveled during this gesture stroke, we need to calculate the length of the orange line connecting the dots. To do this, we will calculate the Euclidean distance between each pair of consecutive points that you see using the formula here. Let's look at an example together. We're going to calculate the distance between the second time point and the first time point. At time point 2, the X position is at negative 0.774. At the previous time point, the X position was negative 0.775. If we take the difference between these two X positions, we see that the distance on the x-axis was 0.001 units, obviously a very small movement. Now we'll calculate the difference of the y position between the second and first time point. This gives us a vertical distance of 0.005 units. If we plug these two numbers into our Euclidean distance formula, we find that the 2D distance between the second and first time point is 0.005 units. Using this formula, we can continue all the way down, calculating the Euclidean distance between each step. The total distance traveled for a given gesture stroke is the sum of all step distances between the consecutive points. In this case, the total distance traveled was 1.81 units. A concept that is related to distance is displacement. Displacement is the shortest straight line distance between the starting and end point. Displacement is a vector, which means that it has both magnitude and direction. For example, 1.2 units left. Let's look at an example of displacement using the same gesture stroke. Displacement is the length of this orange arrow. In this case, we only care about the net change in position. So we take only the starting position and the end position. Looking at the change in position, we can see that the right wrist moved 0.275 units on the x-axis in the positive or left direction, and 1.2 units on the y-axis in the negative or downward direction. If we follow our formula for Euclidean distance between 2 points, we see that the total displacement of the right wrist for this gesture stroke was 1.23 units. The vertical change was much larger than the horizontal change. So when we describe the direction of the displacement, we could qualitatively say that the gesture stroke was produced primarily downward and slightly to the speaker's left. Now let's look at the definitions for speed and velocity. You might sometimes hear these used interchangeably, but there is a difference in their definitions. Speed is the change in distance over time, which is a scalar value with only magnitude but no direction. In contrast, velocity is change in displacement over time, and this is a vector with both magnitude and direction. If we wanted to, we could calculate the average speed or average velocity for this gesture stroke. This gesture stroke was 890 milliseconds long, or 0.89 seconds. Although the denominator is the same time for both formulas, the total distance traveled on the left was larger than the magnitude of the displacement on the right. So our numerators are different. This gives us an average speed of 2.03 units per second and an average velocity of 1.38 units per second. And again, we could describe the direction of the velocity as downward and slightly left. However, during this gesture stroke, speed and velocity are not constant. What's going to be more interesting for us is calculating the instantaneous speed of the right wrist at each moment in time, because we are interested in how the wrist might change speed throughout a gesture stroke and identifying the moment of peak or maximum speed per stroke. We can calculate instantaneous velocity in just one dimension. For example, here, we calculate only vertical velocity at each moment in time using the change in position on the y-axis only. Negative indicates that the wrist is moving downward, and positive that it is moving upward. The difference in y position between two time points is the numerator, and the change in time for each step is the denominator. In our case, this is 10 milliseconds or 0.01 seconds because our sampling rate is 100 hertz. The values that you see in the vertical velocity column are measured in units per second in our normalized coordinate space. We can also calculate the 2D speed at each time point, considering both change in x and y. In this case, the numerator of the formula is a Euclidean distance between the 2 points, and the denominator is still change in time, so 0.01 seconds. Because the movement for this stroke is mostly on the vertical axis, there's not a huge difference in the values between vertical velocity and 2D speed. But we do see that the speed values are always higher because we're considering movement on both x and y axes. However, one big difference is that the value of speed is always positive because we don't take directionality into account. Again, our speed measure is in units per second because we've factored in our video frame rate to make it more interpretable. If we plot the speed of the wrist over time, we see that it changes quite a bit throughout the stroke, and our peak speed is 4.24 units per second, occurring around 24,700 milliseconds. This can help us identify the moment when a gesture is most kinematically salient and how much effort was expended. Indeed, if we find this time point in the video, we can see that it is right in the middle of his downstroke, and there's quite a lot of motion blur corresponding to this fast movement. We can even plot our original stroke trajectory with the color of the points showing instantaneous speed. This allows us to easily visualize how speed changes over time and as the participant's wrist changes position. At the start of the stroke, the wrist speed was close to 0. It moves slowly upward before quickly moving downward and finally slowing down again as the wrist comes to a resting position at the end. Mathematically, velocity is the derivative of position with respect to time. The derivative represents the rate of change of a variable, in this case, position. And it can be interpreted as the slope of the position curve at a given moment in time. So this plot shows the y position of the right wrist over time. This is a zoomed in section of the stroke where the speaker's wrist first begins to move down. Now I've highlighted 4 pairs of consecutive points in black. If I draw an arrow estimating the slope of the line between each pair of these black points, we can see that the rate of change in vertical position is not constant. It changes over time. A flat slope would indicate that there is little to no change in vertical position, whereas a steep slope, as we see around 24,700 milliseconds, indicates that position is rapidly changing over time. The direction of the arrow reflects whether the wrist is moving upward or downward. However, for our analysis, we will mostly focus on speed, which considers only the magnitude of change in position. I want to highlight a small difference in how we've calculated position derivative in this lecture compared to how we actually do it in the Jupyter Notebook tutorial. In the examples in this lecture, we calculated the difference in position between the current point and the next point, which allows us to estimate the velocity between points. This approach to estimating the derivative is called forward difference because it uses the point directly ahead. This approach is simpler mathematically, so we've used it to illustrate these examples. However, in the notebook tutorial, we estimate derivative using a central difference approach. Rather than estimating the slope of change between 2 points, this approach allows us to estimate the slope of a curve at a given point by calculating displacement between the neighboring points on both sides. Whereas the forward difference approach allows us to estimate velocity between points, the central difference approach allows us to estimate velocity at each time point. Because the central approach looks both forward and backward, it is a better estimate of the true slope and reduces bias or error from calculating in only one direction. Now we've learned that velocity is the derivative of position, measuring how position changes over time. We can actually calculate more derivatives. For example, acceleration is the change in velocity over time. If we increase our velocity, we accelerate. For example, pressing the gas pedal in a car. We can also decelerate by slowing our velocity to a stop. When we gesture, our velocity is never constant. Acceleration allows us to measure how quickly velocity changes, which is related to force and movement control. Similarly, jerk is the change in acceleration over time. This is related to how smooth or abrupt a movement signal is. For example, high-frequency fluctuations in jerk might reflect tremor or movement instability. In gesture research, these higher-order motion features can help us study how dynamically or smoothly gestures are produced. We can also look at how these kinematic measures pattern together. If you look at this plot, it shows the X and Y position of the right wrist for the first 10 seconds of one of our videos. The bottom plot shows the speed, acceleration, and jerk curves for the same time period. These measures are on very different scales, so we've normalized them to a z-score distribution so that we can more easily visualize them together. And one thing that is important to know is that each time you derive a new measure, high-frequency noise can be amplified. So it's important to apply a smoothing filter between each step. We will be focusing on only speed and velocity in our Jupyter Notebook tutorial, but these higher order kinematic measures may also be of interest to you, so if you want to learn more, we'll link to an EnvisionBox module in the description. In this lecture, we're describing movement using positions tracked from video, such as the X and Y coordinates of the wrist moving across the screen over time. From these position traces, we can calculate velocity, acceleration, and other motion features. To compare participants, we also normalized body size and position so that everyone is represented in a common coordinate space. However, it's important to note that this is different from how movement is often represented in biomechanics or motor control research. In those fields, researchers frequently analyze joint angles instead of screen positions. For example, how much the elbow bends during a reach, or how quickly the shoulder rotates. Those measurements use anatomical reference frames tied to the body itself and usually require 3D motion capture and skeletal modeling. The 2D video tracking methods we use in this lecture series mainly describe how body points move within image space or in a normalized coordinate system. These measures are useful for studying gesture timing and movement dynamics, even though they do not provide a full anatomical model of movement. Throughout this lecture series, we will very briefly highlight a few papers that use the kinematic measures that we're talking about. This is certainly not an exhaustive literature review, but we want to give a few examples of the research questions these measures were used to address. So in this study, participants performed object-related instructions, for example, pour the water into the glass, either by gesturing or by physically acting on the objects. The authors wanted to know whether communicative intent changes movement kinematics for gestures and actions. They looked at a variety of kinematic measures, but one measure was peak velocity, which they defined as the maximum speed reached by the dominant hand during a movement. They found that participants produced gestures with significantly higher peak velocity and high compared to low communicative contexts, but this was less the case for actions, where peak velocity did not significantly differ between conditions. And now let's turn to our Jupyter Notebook tutorial, where we can calculate speed and velocity together. Okay, let's navigate to the Lecture 7 script folder and open the Jupyter Notebook for this tutorial. Select your kernel and choose KLS Environment. In this notebook, we'll be calculating horizontal velocity, vertical velocity, and 2D movement speed. Up until now, we've been working with position data, but now we'll convert position data into speed and velocity to quantify how quickly position changes over time. So first, we'll set up our workspace. Let's run this cell to load in our packages. Next, we'll read in our data. We are reading in the merged data CSV file that we created at the end of the Lecture 6 tutorial. Run this now, and you can see the preview below where we have participant metadata, motion tracking data, speech amplitude, and ELAN annotation columns. Now in section 2, we're going to compute our first kinematic measures. Let's start by visualizing the original position data. We'll look at just the first participant in the dataset and plot the X and Y position of their right wrist over time. Run this now. These curves describe how the position of the hand changes over time. You can see that sometimes we have very rapid changes in position, and other times it is more gradual. Sometimes the change in position is mostly on the y-axis, and other times it's mostly on the x-axis. So let's quantify this change now. In this markdown section, I put some reminders from the lecture about how speed and velocity are calculated and definitions for the different measures that we discussed. At the top of the code cell, we define a function called calculateDerivative. Derivative measures the rate of change of a variable. It will take into account our sampling frequency, which determines the change in time for each row, and we use the central difference approach to identify the slope of change in position at each time point. Then we are defining the name of our time column, a list of the joints we want to calculate velocity and speed from, and which dimensions we're interested in. So for us, that includes only the x and y dimensions. Using the data frame we read in above, we will loop through each unique video file and then calculate the derivative for each joint in our list using the position values for that joint. We create new columns for velocity and the x dimension and y dimension for each joint. This corresponds to horizontal and vertical velocity. Then for each joint, we calculate 2D speed by combining horizontal and vertical velocity into a single measure that captures change in xy position over time. So in other words, we capture how much the hand is moving diagonally through space without considering the direction of movement. Let's run this code now. We save our new columns to the data frame, which you can see previewed below. So to start, we have the motion tracking position data for all of our joints. But if we keep scrolling, we see that for each joint, we have 3 columns with the prefixes val x, val y, and speed. So for the right index fingertip, we have a column showing its horizontal velocity, vertical velocity, and 2D speed. Let's run this next cell and save our updated data frame to a CSV file in our output folder called mergedatakinematics.csv. Again, if we navigate to our Lecture 7 output folder and open it up, it looks like this. And we have our position data and speed and velocity data for each joint. For the last section, we're going to visualize the results. We are going to select data from one of our videos, in this case the cheeseburger video, and visualize the horizontal velocity, vertical velocity, and 2D speed of the right wrist over time. So let's run this. And because this plot is interactive, we can click the different labels in our legend to make them disappear or come back. So let's focus first on vertical velocity. On the y-axis, we are measuring change in units per second in our normalized coordinate space. So if vertical velocity is large and positive, it means we are moving quickly upward. If it's large but in the negative direction, it means the hand is moving quickly downward. Now let's look at horizontal velocity. In this case, large positive values means the hand is moving quickly leftward, and large negative values means the hand is moving quickly rightward. Now if we look at 2D speed, we see that it has only positive values because, again, it quantifies the magnitude of change in position, but not direction. In general, for all 3 line plots, when you see peaks, it indicates that the hand is moving fast, and we would expect these peaks to be occurring mostly during gesture strokes. Because we also have our Elian annotations loaded in from the previous tutorial, we can also calculate some summary statistics for each gesture stroke. We are going to calculate the mean 2D speed and the max 2D speed of each gesture stroke. We will also use the annotations in our hand column to determine which hand to take into account. So if it's a right-handed gesture, we will calculate mean and max speed of the right hand only, and the same idea for the left hand. But if it's a two-handed gesture, we will calculate mean speed as the average of both hands and max speed as the largest value produced by either hand. We're going to create a smaller data frame where we store kinematic measure calculations for each gesture stroke, which we'll save to our output folder so that we can add columns to it in future tutorials. So you can run this now. and in the preview, each row corresponds to a single gesture stroke ID, but we also have our participant metadata and information about which gesture unit ID and hand the stroke belonged to. And you can see our new columns for mean and max speed for each stroke. So this is the type of data frame that you might use for statistical analysis if your dependent variable is speed. If we go to our course folder and look at the Lecture 7 output folder, we will see that we have two CSV files saved now. One for the full merged dataset with our added columns storing speed and velocity calculations, and our smaller subset data frame summarizing kinematics of individual gesture strokes. Now we're going to explore the speed data a bit more using some visualizations. First, I'm reading in a screenshot to remind you about our group variable in our data frame. Each participant belongs to either the pattern group, meaning that they are wearing clothes with patterns, or the no pattern group, meaning that they are wearing solid colors. This is a really silly example that is just for demonstration, but let's see whether there are any group differences in gesture speed. For example, we could ask, do participants wearing patterns gesture faster than those wearing solid colors, or vice versa? In this next code cell, we are creating two box plots to visualize group differences, one looking at mean gesture speed, and the other looking at max gesture speed of the wrist. Let's run this now. Although we are not doing any statistical tests on this small dataset, you can see just by visualizing that there is a lot of overlap in their box plot distributions for mean speed. And this is what we might expect since our grouping variable is pretty random. One thing that's nice about these interactive plots is that you can hover over a dot and it will tell you what video and stroke ID it belongs to. This is really helpful for checking that the results make sense with your raw video data. For example, let's look at this point, which has the highest mean speed of all the gesture strokes in our dataset. It says it is the cheeseburger video and stroke number 14. So let's pull up that ELAN file from the Lecture 6 script folder to see how fast that gesture looks. If I play the stroke in the ELAN file, we can indeed see that the hand is moving very quickly. If we scroll down to look at the maximum gesture speed, we again see a lot of overlap in the two distributions. Cheeseburger, stroke number 14, also has the highest max gesture speed of all the strokes in our dataset. And that's it for this notebook tutorial. We have now quantified not only where the participant's hand is at a given moment in time, but also how fast it is moving. We'll use these speed data in future tutorials to identify speed peaks, gesture submovements, and holds. So these calculations are very foundational for the rest of our analyses. In this lecture, we learned some key definitions and measures for the study of kinematics. We learned how we can derive speed and velocity from position data to quantify not only where a speaker's hand is at a given moment in time, but also how fast it's moving and how that position changes over time. Measures like velocity, acceleration, and jerk reveal the temporal dynamics of how gestures are produced. In the next lecture, we will look at another application for analyzing gesture speed. We will use the calculations we made today to quantify how peaks in gesture speed correspond to peaks in speech amplitude or loudness. This is a measure of speech-gesture synchrony. As always, thanks for following, and we'll see you next time.